utility life and went into consulting. So I hope you all had enough about excavation, because we're not going to talk about excavation at all. No excavation in this closure technology. So we're going to talk about discrete in-situ solidification as a closure option, and I just wanted to see who's in the audience is familiar with the in-situ solidification, also called ISS. Good, so I can go quickly through the introductory portion of this. So there's sort of two elements to this. There's a closure technology overview, which is sort of a holistic approach to closure, which relies on containment, both groundwater containment from a horizontal and a vertical standpoint, and then also a case study where we're implementing this technology at a plant in the Midwest for a undisclosed utility. Pardon me? F5. F5. Wait, put my glasses on to see F5. I'm not that familiar.
You gotta go to presentation mode.
Presentation slide. I got it. I got it. Do I have to start over? Thank you. Okay, so the objectives of the talk to present this closure technology, which minimizes groundwater infiltration to the maximum extent feasible, which is in the EPA regulations, and I'm sure we all know about. It's permanently technically sound, minimally disruptive, and it's cost effective. And this is sort of the agenda outline. There's an overview of the closure technology, the proof of technology, the project that we're working on, the case study, the cost evaluation, a little slide on stakeholder acceptance, and then you all can ask me a bunch of questions. So ISS, in-situ solidification, for those who don't know what it is, it's that in-place mechanical mixing of media. Could be soil, could be ash, with dry reagent or an engineered grout. The goal is to decrease permeability and increase strength. Reagents are typically Portland cement, slag, cement, bentonite, lime. Those are some of the reagents that we've evaluated. Performance criteria is generally to increase permeability to less than 1 times 10 to the minus 6 to 1 times 10 to the minus 8 centimeters per second. That's sort of dependent on the regulatory agency, and to increase compressive strength to greater than 50 psi. So for our technology, we use conventional, fully penetrating ISS columns, and then also discrete zone columns, which is a sort of a emerging technology. So there's our typical crane-mounted drill rig. This is a fully penetrating column, which goes from the surface all the way down to your target zone. This is similar to the presentation earlier this morning. This is a way to establish containment for vertical groundwater flow, similar to the story walls. And then we have discrete zone ISS, and with overlapping columns in the discrete zone, you basically create a liner which mitigates vertical horizontal flow. So I think this next slide, this goes into an animated presentation that's about 3 minutes long, and it will give you an idea of how this works. It's much more effective than me trying to stand up here for 3 minutes and talk to you about it. So can dim the lights, and I can answer any questions after the video, but hopefully we'll give you the feel for the technology.
Here we show a typical ash impoundment constructed within earthen berms along a water body. The ash is in
There's
contact with
supposed to be
groundwater
sound
which
with
flows
this, and the guy
horizontally through the
promised
ash,
me the
discharging
sound
to
would
the water
work.
body, and fluctuates vertically in and out of the ash. Our technology uses two types of in-situ solidification, or ISS, methods to achieve closure. Initially, fully penetrating ISS columns are installed in a section of the berm area. Media is mechanically mixed with an injected reagent, generally a cement mix, to increase the strength and reduce the permeability of the media. Full-length columns are generally mixed 3 times from the surface to the total depth to achieve good homogeneous mixing. After completion, the full-length columns around the perimeter of the impoundment provide structural stability and deflect the horizontal groundwater flow in and out of the impoundment. This ISS method is similar to slurry wall construction. The second ISS method used in our technology is the construction of discrete ISS columns at the bottom of the impoundment at the interface between the ash and the naturally occurring material, which we refer to as the discrete zone. The discrete ISS columns are installed either concurrent with or soon after the full-length column installation. Ash is mechanically mixed from the surface to the top of the discrete zone, where a reagent is then injected and mixed in the discrete zone a minimum of 3 times. The construction of these discrete zone columns continues throughout the bottom of the impoundment, with each column overlapping the adjacent columns. This overlap is confirmed with a real-time quality control system which documents the width, depth, and verticality of each column. The continuous discrete zone can be engineered and constructed to meet various criteria and performance standards. The continuous discrete zone creates an impermeable barrier below the saturated ash that eliminates groundwater infiltration vertically in and out of the impoundment. A plan view of the completed impoundment shows fully penetrating columns along the perimeter that provide structural support and mitigate horizontal groundwater flow in and out of the impoundment, and the discrete columns in the interior that mitigate vertical groundwater flow in and out of the impoundment. Concurrent with ISS construction or soon after, the impoundment is capped in accordance with state and/or federal requirements. Capping, in addition to implementing the full and discrete ISS, provide complete encapsulation.
So anyway, are there any questions on that? I apologize that the video did not.
So with doing that, once it's complete, does the original containment no longer become regulated dam?
I don't.
Because most of those are regulated dams, so that you would have to maintain dam safety permits for the life of the basin.
So anyway, the next slide is the proof of technology. This technology, full ISS, has been around for a couple decades. Been used on circular and record sites. It's been implemented at CCR impoundments, and then the discrete ISS was demonstrated at a circular site. We piloted at this site last year, and we're starting full scale next month. So I talk about the case study a little bit, or this is the site that we're working on. I'm going to talk about the conceptual site model, the objectives, the summary of the pilot study activities we did last year, and where we are currently. So this is the general site layout. We have limited horizontal groundwater flow because we have a confining layer in this area from pre-existing conditions. It's all a glacial outwash. There's areas in this impoundment where the confining layer is absent or the ash is deep. And this is problematic when the river rises, the potentiometric pressure causes vertical migration of groundwater in and out of the impoundment, which the regulator said needed to be addressed. So the options to the client were basically, you can dig up this entire 135 acre ash impoundment, or you can fix this. Ash is, the scale on this is sort of exaggerated just a little bit, but ash in this area is up to about 60 feet deep. So basically, this is a little different than the animation. The animation was to address both horizontal and vertical groundwater flow. The project that we're working on is just really to address vertical groundwater flow, which has been a problem at many sites and something that EPA is anxious to have people address. Our impoundment objectives were to construct engineering control to minimize to the maximum extent feasible movement of liquids from all directions. So we had our natural clay layer that inhibited horizontal migration, and we had our plan to install this discrete zone to eliminate or mitigate vertical migration. The objective was to gain stakeholder approval, which we did through a series of public meetings and notifications, and to reduce the cost and schedule to achieve closure. So basically, what's the fix? We're installing a 4-foot thick, low permeable zone in this area to address the vertical inflow. And then there'll be an engineered cover to cover the surface and create a pretty much containment zone. So things that we've done so far at the site, we did a couple of rounds of field investigations to evaluate the feasibility of the technology, did a basis of design report, we did bench scale treatability studies to determine different mixes for the different types of ash and different types of underlying material that we were going to select for our discrete zone. We did a pilot study. Actually, the guys from Forgin were the contractors that did the pilot study last year out there for us. We finalized the design. We assisted the client with contractor procurement, and we procured a contractor, which unfortunately wasn't Forgin, but that's okay. And we're getting ready for full-scale implementation. We had 8 contractors bid on this project, and this, just for total transparency, this is the first time full-scale this has ever been done, this technology. But we knew it could be done. We knew we had contractors that were smart enough and knew how to do it, had the experience that they could do it. Pilot study objectives, we wanted to evaluate drilling methods. This was basically drilling methods to get from the top of the ash impoundment down to the discrete zone. We wanted to evaluate our treatment effectiveness with our different mix design. We wanted to evaluate productivity because, as Don was talking about, it's all about productivity. You know, how fast can these guys go? And because this had never been done full scale, we were like, I don't know how they can do it. So we evaluated that, and we evaluated our quality assurance procedures, which was a major thing because, as was talked about in the story wall discussion, you can't see what you're doing. You can't see your little discrete column. Well, they're not that little. They're 12 foot in diameter, but they're 4 foot thick, but they're 60 feet under the ground, you know, and so how do you see this, and how do you know that the next one you put next to it is overlapping the one that you just installed? So that's a little tricky. We'll talk about that a little bit. So this is an area. This is our 35-acre area in the whatever color that is. And then we had 3 areas where we did our pilot study, and it was based on different material and different depths. So we had one area. I'll just go through these really quickly because I'm probably running late on time. This area was pretty straightforward, pretty shallow. Fly ash, about 30 feet below grade. Each one of those circles is a column that was constructed. This area was deeper. This was ash in 55 to 60 feet below grade, and also predominantly fly ash. This area was a shallow area of bottom ash that we evaluated. So in summary, we did 61 columns. We did single columns to look at mostly reagent list drilling fluid. We did 5 groups of 3 columns to evaluate overlap. We did 1 group of 7 and 2 group of 8 to basically evaluate productivity. We evaluated 5 drilling fluids, 2 auger sizes. The discrete zone was reached at all locations. We did 3 sampling techniques. We sampled the discrete zone 4 feet thick. We needed to collect wet samples of that zone. So that's also a little, takes a little bit of skill to do that. Fortune did a great job. We looked at 2 water ratios for our mix, collected 17 samples. Column completion ranged from 25 to 60 minutes. And we demonstrated that our quality assurance system provided reliable information. And that's really important. And the next slide gets into that detail. This is the output from the dialogue system that is on the rigs. This is a Gene Luntz system. There's a couple other manufacturers and developers of this technology, but so far these guys are far ahead of everybody else. It monitors your depth, monitors the amount of grout that you're putting in the hole. Here, in this case, this is all fluid getting through the reagent list drilling zone is what we call it, and then down here is actually where you start to inject your grout mix. The most important part of this output for us is this part right here, deviation Y and deviation X. This is a really bad slide as far as clarity, but this is in inches. And this tells you basically how many inches your column has deviated from your starting point at the surface. So this is the information that you need to get on a real-time basis to make sure that your next column, you don't change your column layout day to day, but you want to make sure if you have a hole in your liner or between your columns that you go back and you fix that hole. This is also the output from the system, and over here we have the depths, 30 feet, 31.8. So these are the columns. This is the output that's important because this is where your reagent is and where you're creating this low permeable liner. So you want to assure that you have overlap in your columns down at the base where you're installing your low permeable zone. Cost evaluation, I'll run through this really quickly. And this cost evaluation goes back to the original slide that didn't have audio. But it's with the fully penetrating columns around the outside and the discrete zone at the base. And these are the assumptions. So we're going to look at excavation, full ISS, and discrete ISS. So we have an impoundment that has approximately 1.3 million cubic yards. It's 40 acres, it's 20 feet thick, and the bottom 5 feet is saturated. So your assumptions for excavation are you're going to dig it all up. And you're going to transport it some distance away, and the impoundment has to be backfilled. And you have to dewater. Real pain in the butt, dewatering it sounds like. Full ISS, your ISS in the entire 1.29 million cubic yards. No dewatering. Impoundment will be capped with swell. There's no swell. I know my sound didn't work. This is not the updated one. Our pilot study indicated you don't generate any swell. You have this hydraulic compaction actually with the ash. Once you start injecting water, the ash sort of compacts itself. We actually lost material in most of our columns in our pilot study. We didn't generate well, which you would normally do on an ISS project if you were just dealing with soil. For the discrete ISS, we're only doing ISS at 366,000 cubic yards because you're doing the perimeter and you're doing the 5-foot thick zone at the bottom. So typical cost categories: general conditions, dewatering, excavation, ISS, and site restoration. The general conditions, we kept these basically the same to just for apples to apples. This is the these two up here are the dewatering. This excavation and transportation should be blue because they didn't update this. They're not blue. But anyway, basically excavating and transporting all the ash. Once you get into the ISS treatment, we assumed $1 million for ISS equipment to be mobilized. Full-scale ISS is about $70 a cubic yard, comes out to about $90 million. Discrete ISS is in the neighborhood of 100 cubic yards because there's cost associated with getting to that zone. But your final numbers, you can see the excavation, off-site disposal, and full ISS are similar in the range of 98 million, and discrete ISS is less than half of that at about 43 million. So those are numbers based on our scenario for our full scale. The numbers for, there was supposed to be another slide here. The numbers for the site that we're working on, the utility provided a number of, if they had to excavate 135 acres, which the state agency said you either excavate 135 acres or you discrete ISS 35 acres. The utility estimate for excavation of 135 acres was between $300 and $400 million. Our contract estimate for the discrete ISS with the remedial contractor is $50 million. So if you look at that comparison, it's pretty significant. And I think the opportunity is there to address vertical infiltration and not have to address the whole impoundment, and it was done at considerable cost savings to utility. So just running through real quick, these stakeholder goals are similar. Most of the stakeholder goals have are similar. We have impoundment owners, regulators, public environmental groups, public ratepayers. Technology controls groundwater impacts both horizontally and vertically. This helps to prevent catastrophic failure along berms, avoids impacts, other environmental impacts from ash handling, dewatering, minimizes cost of closure. We're looking at probably 2 years of discrete ISS to close that 35-acre area. Meets regulatory requirements. We've met with both EPA and the state agency to discuss this site, and both have approved the approach and this timely implementation of closure. Key points: eliminates groundwater infiltration both vertically and horizontally, increases impoundment stability, eliminates the need for CCR removal, reduces cost and risk, provides environmental benefits, and relies on proven technologies that there are people out there that are available to implement. all I got. Thank you. And I will take questions, and I apologize that the video didn't have sound, but if you want to listen to it, you can go to our website, and you can pull it up. There's a little one-page flyer on the technology, and there's a link to the animation that has sound.
All right, thanks. Is there contact information up there? In case some people want to get a hold of you and learn more about this thing.
I can.